Welcome back to Young Engineers of Today. I hope you had a good weekend, and I hope you're ready to actually finish up model rockets, because that's what we're going to be doing today. We actually have less material than I thought we did, so this is going to be a short class, and we're probably going to be moving on to a new subject on Wednesday. Now, it might come to pass that I'll find some more material to at least finalize, well, at least add on to model rockets or something like that for Wednesday. It's possible, but as it stands right now, we don't really have an entire class's worth of material with the remainder of the information, and if we don't have it today, we certainly won't have it on Wednesday, for an entire class. So regardless, we're going to start covering new material on Wednesday. So for all of you who were maybe a little bit less than thrilled about all the stuff that we've been covering in model rockets, rejoice. You're almost out of the woods. If you enjoyed it, well, hopefully you've been able to take something away from this, and it's given you some perspective on something that you might want to, I don't know, look into for a hobby or to pursue for later on in life. Who knows? No pressure. But but anyway, like I said, this is probably not going to cover the entire class. It actually took about 35 minutes with my middle school class, so chances are it's probably going to take about as long with you guys. We'll leave it open for question and answer time afterwards, as we always do. We'll do the poll questions like we always do. It's just going to be a nice short class, so go ahead and enjoy it. Take the opportunity to get stuff done that you need to get done. Relax in the fact that you have like at least a half day insofar as extracurriculars are concerned related to young engineers. I don't know what's going on in your life. You could have a lot of stuff, and we'll get through this, and hopefully it'll make some more sense by the end. So yeah, this topic is specifically about things to consider on and before launch day, things to think about, basically the way the rocket. You'll see what happens, what it's about. So this covers the size of the launch site that you might want to have, anticipating how high your rocket's going to fly, and actually determining how high your rocket flies. So this is why it's things to consider on and before launch day. So much of this, now that we've seen much of the design philosophy that goes into creating a model rocket, why you would want to pick a particular fin shape or size, or an engine size, or a nose cone shape, or recovery type, whatever. Now that you've gotten a feel for why you might want to pick something in particular for a model rocket, it's time now to sort of get a better idea as to what's actually going to happen when you launch it, and what you'd want to look for, what you want to account for, determining how high your rocket went, things like that. It's also important to note, as a side note, this will come up a couple of times throughout the presentation, that air will always affect the rocket trajectory, and wind especially so. So wind will always make your rocket fly at least somewhat laterally. Sometimes, and oftentimes when you're first launching, further than you anticipate. You might think, okay, it's going to go straight up, when in reality it ends up landing 50 feet away, 40 feet away from the actual launch pad. Between the ascent and the descent with the parachute or whatever, it ends up being a bit off the mark. So for that reason, you need to figure out how much of a launch area you would need for your rocket. And we've got a bit of a diagram here. It's probably a little bit small to read, but it does provide a baseline for a minimum launch area for a rocket. Let's take a look at it. So as you can see, each area is a square. That's just obviously for representational purposes. Your launch area doesn't have to be a square, but this gives you a general idea of the area. So at quarter A and half A, you can see that each of the sides are about 50 feet in length, which gives an area of about 2,500 feet squared, or 2,500 square feet. So we're talking like a townhouse or something like that. The floor area of a townhouse. If you have like a nice like 2 bedroom, 2 bathroom, 3 bedroom, 2 bathroom townhouse, uh, you're looking at 2,500 square feet, that kind of thing. That's actually a decently sized house. So imagine, like the house you live in and take all of the rooms and then lay them on the same floor out in roughly a squarish shape, and then you should have some idea of how much like a quarter A or half A engine would need in order to safely launch. Now, the math isn't exactly perfect, but it's a good rule of thumb to assume that for each engine class, on top of that, you double the length of the sides. So quarter A and half A are 50 feet on a side, Class A is 100 feet on a side, Class B is 200 feet on a side, Class C is 400 feet on a side, and so on and so forth. Now, obviously, because we're talking about squaring things, when you double the length of a side, you quadruple the area that it takes up. You start talking about areas of 10,000 square feet and 40,000 square feet, and 40,000 square feet is just for Class B engines. A Class C engine, you're looking at 160,000 square feet. That's a lot. That's probably, it can be too much, but it's a lot of area. Um, you, it really depends. I mean, you could get away with launching a C in a smaller area on a calm day, but if you're anticipating normal winds and stuff like that, you probably want to make sure that you've got enough of an area for it. But yeah, notice how you quadruple the size of the area with each doubling of the sides. Ha! Math, because that's just how math works. So the other thing to keep in mind is this is a recommended minimum. It's a lot of space. It's a lot of space. And you would need more space if the wind was actually blowing that day. So it's important to note that wind will really do a number on how your rocket flies. In fact, it's enough that you have to be very careful about when you launch. If it's too windy, you probably don't want to launch at all because you're going to lose your rocket if it goes high enough up in the air. In fact, the higher a rocket goes, the more it is affected by the wind for probably obvious reasons. But, if the wind is blowing, it's not just blowing at like human height. It's also blowing at skyscraper height. And in fact, it's generally blowing harder at skyscraper height because there are fewer things to slow the wind down. And, the different high and low pressures and stuff like that you'll actually feel them more up in higher altitudes. Even when we're talking, a few hundred feet. But, the wind is always blowing at any height. So as a rocket is flying upwards and almost lost my headset. As the rocket is flying upwards and then back downwards, you're going to have to deal with the fact that the wind is blowing on the rocket the entire time it's doing that. So if it's flying higher, it is spending more time being affected by the wind, which means it's going to get further and further off course. So you have to think about that. In addition to the fact that the higher up it goes, the faster the wind is blowing because there are fewer obstructions slowing the wind down. So it's going to be even more affected on top of that. So for that reason, you want to be very careful about the wind conditions whenever you launch a rocket, especially if your rocket is launching decently high. These are things that actual aerospace engineers and launch technicians and stuff like that, those are the kinds of things that they have to worry about with full-size rockets. If the day is too windy or the weather is too, unstable, they'll just go ahead and scrub the launch for that day because they don't want to have a rocket be blown off course or even worse, toppled. I mean, blown off course, if you're flying to space, whatever, but you're going to have to expend fuel in order to return to the point that you were originally anticipating. And a lot of times they're dealing with very very slim margins of fuel in order to save on cost and things like that. So anyway, there is rocket simulation software out there. Oh, whoa, what? That is way, okay. Oh, so it's important to go into this having an idea of not only wind conditions, but how high your rocket should be going. That's right. I forgot about that segue. So there is rocket simulation software that can determine how high a rocket is going for us. I mean, we used OpenRocket, so you guys are familiar with it at this point. And it it's simulated all the sort of the lifetime of the rocket flight and things like that. But it's also it's good to have a general idea of how high rocket engines go based on their class. Just going into it, like if you go into it and going like, oh, I'm going to build a D-class rocket, you might want to know, even before you start simulating it in something like OpenRocket, how high, like what kind of height you can achieve with that class of engine. Now there's also sort of a general rule as far as height is concerned when considering motors. Now this isn't really as cut and dry. This is just more sort of a, like the other one is, it's nice and easy. It's, double the length of a side on the launch area for each class of engine. This is not like that. It's not like there's any cut and dry math or anything like that, but this is sort of just a chart that you can refer to that gives you a general idea. As you can see, like we're looking at like 475 feet or 145 meters for Class A, and like 270 meters for Class B, and 440 meters for Class C, and stuff like that. But these, it's important to note, these are best case scenarios. Like, these are absolutely the highest that a rocket would be able to fly, given like a high performance engine and things like that. So chances are your rocket is not going to be flying that high, even if you have one of these engines installed. So why might that be? Like, why would you think that maybe your rocket's not going to be able to go as high as that chart provides? Because, for instance, when we were doing OpenRocket, I'm pretty sure our Class A rocket got to like just around 100 meters. Like it wasn't 145 meters like this thing is saying that, Class A rockets can reach. So why do you think that's the case? Well, okay, so weight for one, drag for another. Um, you have slight imperfections in the rocket manufacturing, and that's going to be magnified by drag, and you're going to lose a number of meters in height on that. You could lose like 10, 15, 20 meters in height on manufacturing imperfections. You put the fins on, and the glue job is very sloppy and stuff like that. You could lose a lot of height like that. Um, you make the fins with an X-Acto knife, and you accidentally cut too deep into one of the fins. That can screw with it too. There's some sort of imperfection on the nose cone that can mess with it as well. Stuff like that. In addition, the weights of the materials that you use have to be taken into account as well. So these theoretical maximums they're talking about are highly precision engineered and made to go as high as possible. So they're using materials that are as efficient as possible. They're they're created to exacting detail. They're created very carefully, stuff like that. So making a model rocket with hobby materials, and especially if it's your first time making a model rocket, you're going to run into, well, warts and things like that when you're making your rocket. There's going to be stuff you're going to be like, yeah, this is awesome, and then it gets kind of messed up, and you're like, ah, dang, like, I accidentally glued the fin on kind of crooked. I have to redo it, or it's just going to have to be like this because the glue set, or whatever the case may be. And for that reason, the rocket's not going to fly as high. That's just kind of how it goes. It's not anything to be ashamed of. It's just how it is. Those theoretical maximums are because people who do this for a living and who have made thousands of model rockets in their lifetime and have techniques down in order to do this, have made model rockets specifically to go as high as possible, and those are the heights that are measured. So there's that to keep in mind. But it's a good thing to have because, for instance, when you're talking about like higher class engines, like when you're talking about this G-class engine up here that's 1,300, almost 1,400 meters, or 4,500 feet, when you're taking into account wind conditions and things like that, it gives you some safety. It gives you like a safety net in essence, because you will, there's that old phrase, plan for the worst, hope for the best, or expect the worst, hope for the best, things like that. That would be kind of an example of that, because you would be sitting there going, okay, so worst case scenario, I'd be flying 4,500 feet into the air, and so I would have to, wait for very calm wind conditions in order to ensure that my rocket goes straight up, when in reality, because your rocket's not going as high, you could theoretically run under slightly windier conditions and have it be okay. But it's good to have that sort of safety net, that buffer of speed that you don't have to worry about. So we've talked about how high you could have it potentially go, but how about figuring out how high it actually goes? Well, that thankfully can be very easy. So in order to do that, one of the ways you could do it is you just have a single person on the ground a certain distance away from the launch pad, the launch base. And they have a tool that has a weight attached on the end called a clinometer. It's a weight attached on the end of a string or a stick. And it rotates along a piece of paper or, a piece of plastic or something. But how exactly does a clinometer work? Well, like I said, it's nothing more than a weight on a string or a stick. And it's in front of a surface that has a bunch of ticks marked on it. And those ticks represent different degrees. Keep in mind that this weight, this string, is attached to the center of a sight, or the middle of a sight. And basically the way it works is you look through the sight at whatever you're trying to measure the height of, whether it be the top of a tree, or the top of a building, or the top of a model rocket that is flying through the air. And that weight hangs down because gravity is a thing that exists. And it's going to hang in front of one of these tick marks representing an angle in degrees. And that angle in degrees is going to be the angle that the clinometer is tilted relative to the ground. So it's going to give you an angle, but how exactly does this help? Well, I'm sure you can see where I'm going with this, but we've got 3 points here. We've got the person with their clinometer, we've got the launch pad, and we've got the rocket. And these each represent a point on a triangle, a right triangle, in fact. Ideally speaking, a right triangle, because that rocket will be ideally flying straight up. So we've got a right triangle, right? The person using the clinometer, what they've given us is as you can see right here, they've given us the angle on this corner of the triangle. We know what this one is, right? It should be a right angle. And we also know, because we measured this beforehand, the length of this side of the triangle. Now, I'm sure you guys have taken high school geometry or equivalent or whatever, and you might even be in like pre-calc trigonometry or calculus or whatever. So you're familiar, certainly, with the idea that if you're given a right triangle and one angle and one side, you can figure out the other angle, and you can figure out any other side on that triangle. It's just because that there are a specific set of relationships on all of these parts of a triangle, all these features of a triangle that are all well related, hence relationships, that we've mapped out mathematically so that you can figure out on your own. And it goes like so. This right here, this is theta. This is a Greek letter, tends to represent angles, which again, if you've taken geometry or something like that, you probably already knew. But the tangent of theta is equal to the height of the triangle divided by the adjacent side, or the opposite divided by the adjacent. In this case, the height divided by the baseline. So we measure how far that person is from the launch pad. We say, okay, so you're going to go like 100 feet out, and they measure out 100 feet, and the person stands there, and the rocket launches. They use their clinometer, so now they have the angle and they have the baseline. Now, tangent, like I said, is the relation between the adjacent and opposite sides of a triangle. In fact, it's opposite over adjacent. So let's say, for instance, and again, this is probably a review for you guys. Let's say our opposite side is 4 units in length, and our adjacent side is 5. Well, 4 over 5 is 0.8, right? Now, if we knew this angle right here, and then we were to take a tangent of it, the tangent of theta would also be 0.8, because the tangent of theta is equivalent to the ratio between the opposite and the adjacent sides. Again, nothing crazy or groundbreaking, but it is something it's a mathematical concept that's existed for a long, long time. And thankfully, there are a lot of people out there that are a lot smarter than me that were able to figure that out so that we can take advantage of it now. So the idea is, if we know our theta and we know the adjacent length, well, if we multiply both sides by 5, we get the result we get is the length of the opposite side, right? So that's the basic idea that's going on here. We take the tangent of our angle, which we got with our clinometer, we multiply it by the distance between the person and the launch pad, and we get the height of our rocket. And again, if you're familiar with this kind of stuff, you could use sine to get like the length, the ratio of lengths between the opposite side and the hypotenuse, which is the long side of the right triangle. You could use cosine to get the adjacent side and hypotenuse, so on and so forth. So we're using tangent in this case in order to get the length of the opposite side, which is the height of the rocket. Once we do that, we can actually determine how high that rocket's gone. Now, it's not perfect for a number of reasons. What could mess with this sort of measurement? Okay, well, so first of all, it could be as simple as user error. The person could be not looking at the clinometer, right? On top of that, the ground that they're standing on could be uneven, which would also mess with the final height result. On top of that, the rocket flies in 3 dimensions, so the rocket could actually fly towards the observer, or it could fly away from the observer. And that could mess with stuff too, because if the rocket's flying towards the observer, it's starting to fly over their heads, and so they'd have to tilt the clinometer up more in order to be able to get a line of sight on it, which would artificially increase the height of the rocket. As you can see, it's not even flying as high as this one is. However, because the person is tilted upwards more, the clinometer reads a more obtuse angle, which then means that the height is increased. Or it could be going away, which means it's tilted down more. Which again is the same result but in the opposite direction, so it's a more obtuse angle, which makes it look more like the rocket isn't going as high. So those sorts of things can also mess with it. So you've got a few things that can sort of throw a wrench into this particular method of measurement. But by and large, it's a fairly simple and more or less reliable way in order to get the height of a rocket. It gives you at least the ballpark, which is something you can work with, and it's especially good enough, if you're doing like hobbyist model rocketry and stuff like that. Now, if you're really trying to do like some serious NASA level stuff, you're probably going to want more reliable means of measurement. Probably going to want like an altimeter or something like that. But anyway, you probably want to rely on something that's a little bit more dependable than just the single observer uh, uh, measurement. I forgot the word I was looking for. Anyway, but it's good enough. There are ones that use two observers, but the math on that is significantly more complicated. You have to get the relationship between the two people as well as their relationship to the rocket, and then there's basically triangulation involved, different triangulation, um, and it's a whole mess of stuff. So it's something that if you're more interested in continuing with it, it's something you could experiment with. But as it stands, just getting started, single observer is good enough. But actually, that's that's it for today. Um, So like I said, we're going to be moving on to a new set of topics or a new set of material on Wednesday. So keep an eye out for that. Um, even if there's some last minute conclusion stuff that we end up going over for model rockets on Wednesday, that won't take the entire class and we'll actually get started on new material. So with that, like I said, that's going to do it. I'll go ahead and do the poll questions and then we'll leave it open for question and answer time. So if you have any questions about anything, you're more than welcome to throw them out there, related to the class or not. We can discuss them. We got plenty of time. Otherwise, you're more than welcome to head out, enjoy the half class that we had today, and have a good couple of days, and we'll see you on Wednesday.